So, hello, do you hear me well? Enough? Okay. So, welcome to this second talk about SmaCC. So, John presented you the parser generation part, and I'm mainly going to talk about what you can do with rewriting. So, SmaCC, it's a parser generator, obviously. You can also have AST classes generation, like he showed you. But it's also a RewriteNG with powerful patterns. And that's mainly what I will describe in this talk, but we will also talk about what I'm planning to implement in SmaCC, some upcoming features, and what you could also do with SmaCC if you want to help. So first, a little recap, the parser generation part really quick, because it's fine. Like John already said, most of it. So you have a grammar, and you feed it to a parser generator, and it will give you first like a recognizer, which just tells you basically, yes, you can parse it, and it belongs to the language, or no, it doesn't belong to the language, fix your grammar. And you can get a full-fledged parser, which generates a parse tree. Very simple. Next stage is adding like AST generation through annotations. So it will generate the parser, AST classes, and a generic visitor to traverse the AST. With that, the parser can generate like an AST. Very simple right now. What techniques does it use? Mainly, if you have a deterministic grammar with no ambiguities, really simple, it uses LR, so table-based parsing. It's really nice because it has practical parse time. It only scales on the size of the input program, so really cool. But it does not handle ambiguities. So for that, it uses GLR, but it's non-deterministic. It scales exponentially with the number of ambiguities. So it's quite bad, but hopefully most programming languages are nearly deterministic, so there are few ambiguities and they are resolved locally very fast. So that's good. And actually it works by just, if you have multiple interpretations and multiple rules that could be applied at some point, it will just go through all of them. It's important for later. So the RewriteNG, it consists of two parts, or pattern matching parts, where you have your pattern, you specify it, it finds all the occurrences in your program, and then it transforms it using a transformation rule. Specific part about SmaCC's rewriting engine is its work with Metalevel. If you look at the transformation rule, on the left part of the transformation, you have A and B. A and B are metavariables. It means that they are variable in a logical sense, so they are just labeled until they are matched. Because of that, we have like a two-step matching technique that I will describe later, so you have more confidence in what you are working with. And it's based on a nice theory named parsing as intersection. You will see it tends to be scary, but in fact it is not. And so we can perform automatic source transformation through that. So first, you want to define your pattern. So the pattern is written in the host language. If you want to match C, you will write it in C, and you will insert metavariables when you want to extend the match. Since metavariable can match anything, any construct that can appear at this point, this specific point in the parse where the metavariable appears. But what's nice is we do not have to tell him, oh, you need to match an expression node, you need to match like a function declaration node. It just infers it itself. And obviously, after the match is performed, the metavariable holds the subtree of your program that matches. So, how does it work exactly? So you start by parsing a pattern. It may seem weird, like this, but you will understand. So our pattern is ESUG to the power of 2, because it's better. You need to know when to start your parse, where to start your parse, because you have like probably at least hundreds of rules in your grammar. So you don't want to like have to define every pattern from the start of your program. So you look at the parse table, and it automatically infers what rules can be a start. So once you have that for our little expression grammar, we can start at rule expression or rule number. This is all the rules we have in our grammar. It's purely a coincidence. There are rules that cannot be starting rules. Next part, we go to a Metalevel. And what do we do now? Because it doesn't belong to the host language. So actually we look again at the parse table, and they will tell us, oh, at this point in the parse you can have either a binary node or a number node for the expression rule. And for the number rule, you can have only a number. You cannot have anything else. So you insert basically, you bind the name of the Metalevel, like ESUG, to a type. And the type would be binary or number, depending on what you parse. All of this is done in parallel, since it uses JLR parsing. But what happens once you get to the power of operator? Like the rule number cannot have a power of operator afterwards, so it will be killed. That way we do not get it as a match. And the rest of the parse continues until we get to the end of the parse of our pattern, and we get nice subtrees. And actually these subtrees, I call them abstract matches, because they do not hold the concrete subtree. They only hold the type for each meta variable. And why is it so simple to get meta variable types? Because it's based on parsing as intersection. It's a quite nebulous theory if you read it like this. It's intersection of a context-free grammar with a regular language is a context-free grammar. Really weird. But if you look at it correctly, it's your first grammar, it is your host grammar. For example, if you want to manage C, it will be the C grammar. The second language or grammar is your regular grammar. And this is the pattern, because the pattern is basically like a list of symbols, like the symbols from your previous grammar, with wildcards. So Metalevel works as wildcards. And if you parse this with the first parser, it will give you the intersection. So basically all the rules that can match the pattern. So it's a subgrammar. And this subgrammar, if you expand it, you get all the possible trees for this grammar, you will get the abstract matches I showed previously. So that's why it's just as easy to get the matches as parsing our little pattern with a JLR parser. But obviously now we only have types for the Metalevel. We do not have the concrete like matches, because we didn't match it against the AST of the program yet. So now that's what we're going to do, and we just traverse the program AST, and once we found a node that matches the type of the Metalevel and all the other types in our AST, we get it. So now on the right you have the concrete matches, which matches the number 13 for the first Metalevel and 9 for the second Metalevel. So now, basically we have subtrees of our program that matches what we wanted to find, and we can use it to perform transformation. So, yeah, usually when you have a power of operator, it calls the library. So in HPC, like, it's common to just rewrite it as a multiplication by itself. That's what this pattern is. You don't want a library call each time you want to do a power of 2 operation. So actually, the transformation part will not be parsed. It will just be replaced by the Metalevel subtrees we got before and perform automatic source rewriting. You can also do code like node rewrites, but this is not automated. You need to write it yourself, but there is primitives like replace node, add node to modify the AST. So, what can we do with that? Because that's not the last step. We can do code migration, like John uses this mainly. And we can do refactoring, like a search engine, because basically the pattern matching part, it's a powerful search engine. And we can do code specialization. For example, the last example I showed you, when you rewrite a multiplication, obviously you don't want the user to write the multiplication everywhere. The power off is better, it's like a cool concept, so better it be done automatically. So, what's more that I want to do in my PhD is a refactoring engine and a refactoring DSL based on these syntactic patterns. So, basically, you need to decouple the search engine first from the transformation part, because you want to get like matches, and you want, most of the time you get a match, but that's not exactly all the matches you wanted, and you want to refine the matches. So you want to apply patterns after pattern after pattern to get the nice subtrees you wanted to match first, in the first place. So that's why we want to have a search engine to support features such as like multiple cascaded selection. We want to also have a DSL. This is an example of the DSL we want to write. It looks like Star code, but it's actually not. But since like Smalltalk has a nice syntax, better use it. I also want to perform sequences of refactoring to be able to order them, but you want to have different semantics for when you have a refactoring A that fails. You maybe don't really care that it fails, because it was like to refactor a corner case, and you want to continue. So that's one of what we want. But you also maybe want to do some special thing when like precondition fails, because you know that it can be corrected with another refactoring. And then, like, to finish this presentation, I will talk about like a fun application that you can use SmaCC for. It's hardware generation from SmaCC. So, you know, you have your grammar, you generate the parse table, but afterwards, like for Edge 2020 project, Thierry did like a re-implementation, really simple implementation of the algorithm, which is basically 10 lines of code. So in Verilog it's probably 200, but anyway. And our implementation of the scalar. So once you give him the parse table, it will try to parse the stream. Actually, for this project, the stream is like temperature information or like battery usage information for CPUs that want to perform like HPC, and performance computing. And we want to detect defaults in the jobs. So we parse the stream, and once you get what the pattern you want defined from in the grammar, use for an error, and you warn the user that the monitoring was fine, but you have an error. Some last word, if you want to try SmaCC, it's available on John Grant's Github repository. If you want to take a look at some of the features I will write during my PhD, I will first put them on my development fork, and then maybe integrate it with John's repository. If you want to know more about SmaCC, there is a booklet, actually, available on GitHub. And we also wrote a paper with John about the RewriteNG. So if you want to know more about this, the preprint is here. and you can watch the presentation at XME in 2 weeks. And if you want to discuss, do not hesitate to email us. Thank you. Any questions? Too technical?